Okay. So I think the next couple of speakers, you'll really see that now that real-time proving is no longer feeling like a figment of our imagination, but something that's already attainable, a lot of the researchers are really beginning to pivot their thoughts towards security. So, next speaker, Kev Wedderburn, team lead of the zkEVM team, always kind of thinking about the next wave of sets of constraints and requirements that we need to be, really sort of encouraging all the teams to up level to. So he defaced my beautiful slide here. So rather than just prove it, it's just secure it. So we're going to hear from Kev, and then after that from the cryptography team, Arantxa. And so welcome to the stage, Kev. We're going to be talking about how the road to EVMs is paved with good engineering. Yep.
Testing. Can you guys hear me? Cool. Yeah, there's going to be a bit of duplication with my slides just because we've talked a bit about them. Some parts are a bit spicy, unfortunately, as I've just learned from the previous panel. So what do I want to talk about? I want to sort of explain to you guys why are we shipping zkEVMs, what are the components to shipping zkEVMs, and what are the milestones that we need to achieve to ship zkEVMs. Okay, so what problem are we solving and for whom? Here's a graph that shows the relationship between the gas limit and the resource usage of the builders. So pre-zkEVMs, it's a linear relationship. If you increase the gas limit, the resource usage of the builders increases. Post zkEVMs, it is still a linear relationship. It's a bit higher, and this is because the builders now need to prepare inputs for the provers. Now, there is no pre-zkEVM prover line, obviously, but post-zkEVMs, the resource usage of the provers as the gas limit increases is a linear increase, maybe even superlinear. RPC providers, we sort of have to mention them. I know there's a lot of core devs in the audience. zkEVMs do not help RPC providers. They still need to have the state to re-execute, to collect things like logs. Now, for nodes that only want to validate the chain, currently, as you increase the gas limits, their resource usage also increases linearly. Once we introduce zkEVMs, their resource usage becomes roughly constant as we increase the gas limit. And as you can see, there is a point in time where it does make sense to switch to zkEVMs. When this is, we currently don't know. And one point I want to make is on the gas repricing projects that's happening in Ethereum. This makes resource usage efficient, but there will be some point in time where where it makes sense to switch to zkEVM still. Okay, so one important thing that I want to note is that zkEVMs do not solve state growth. The builders and the RPC providers will still need to have the state. What it does solve is for the nodes that only want to validate the chain, they no longer need the state in order to do this. At the Ethereum Foundation, we have a specialized team, the stateless team, who's also working on solving this problem. So this is a problem that we do want to solve, and we do see it as something that's important. Right, so the TLDR of the first section is that we utilize compute asymmetry in order to have some nodes do little and other nodes needing to do more. And these nodes that are doing little are nodes that we care about. These are the nodes that are validating the chain. So how does this all actually work? Is a good question. The current workflow, as you saw from Justin, I'll show you the workflow that Justin was going through. But currently on Ethereum, a beacon block arrives with the payload. A node validates that the payload is correct using their EL, and this requires state. Then they attest to the block if it's valid. As we saw in Justin's demo, The beacon block now arrives with the payload header. They wait for the proofs to arrive, proofs with an S, which attest to the payload correctness, and then we verify the proofs and attest to the block. So this is the consensus layer, and that's sort of the top of the stack. Now let's just look at all of the stack. If we start at the bottom, we have the snark prover and the snark verifier. For people in the crowd who are not sort of cryptographers, you can think of the snark prover as this component that proves execution for a particular function, and the snark verifier as receiving the proof, receiving the proof, and if the proof returns true, or if the verification returns true, then you can be sure that if you had executed the function yourself, this is the output that you would have gotten. Now, on top of the snark verifier, I've written the virtual CPU for the ISA. What this means is that there is a function that takes in some bytecode, RISC-V bytecode, WASM bytecode, and this is what the snark prover is proving. So if you have a RISC-V zkEVM, what you have is a zkEVM that allows you to prove execution of a particular bytecode, a RISC-V bytecode. These three components together is what we usually refer to as a zkEVM. Now, on top of this, we have the execution layer, state transition function, and this is what your ref, eFrex, gef client will be written in. This is a function that takes a block and a state proof, and executing this allows you to know that the state transition function was correct on this particular block. This function gets compiled to RISC-V, and this is what the zkEVMs take in. And at the top of the stack, as I wrote before, is the consensus layer, and this is the component that takes proofs from the network, verifies the proofs, and if the proofs are valid, they attest to the block. So this is the whole of the stack. I mean, you can sort of go deeper on the snark prover. There are things like polynomial IOPs and PCSs, but I feel like if I start explaining this to this audience, it's probably not going to be super useful. You just need to know that there's a snark prover, there's this component that allows you to create proofs of execution of a particular function. So let's look at the first component. What do we want now? We want open source GPU implementations that achieve real-time proving. What do we want next? We want reliable provers. This means that your GPU implementation needs to be reliable, and where you're hosting the provers needs to be reliable. And what we want later, or technically in parallel, is to be hardening these implementations. The next component is the snark verifier. What do we want now? We need 100 bits provable security with grinding by Glamsterdam. What do we want next? 128 bits provable security with grinding by H-star. And in parallel again, we're going to be working on hardening these implementations. You can also see Arancha's talk, which comes after mine, who will go into more detail as to why we want these things. The next component, which is the ISA, or the virtual CPU for the ISA, we really want this. We really want the circuit that you've created to conform to the ISA spec that you said it conforms to. So if it's RISC-V 32IM, it should support all of the instructions in RISC-V 32IM. And again, in parallel, we're going to be working on hardening security. This is going to be an important theme. You can also see the talk I did at ZISC, where if you're a RISC-V zkEVM, we propose that you support RISC-V 64IM none. The none means that we won't be supporting the Linux syscalls. If you're a WASM zkEVM, you can do whatever you want for now. This proposal doesn't say you have to support RISC-V. It just says that if you are, this is the minimal that we want you to support. The QR code links to the PR with the proposals and sort of the analysis we've done in order to arrive at this conclusion. Okay, the next part is the execution layer state transition function. So this goes to the ELs, the execution layer core devs in the audience. We'd like you to implement a stateless state transition function. So this is a function that takes in a block and the MPT witness. The next part, we want you to ensure that the STF passes east, and this is a minimum requirement. It needs to pass all of the Ethereum execution spec tests. And again, security hardening is something that we care about. And the last layer at the top is the consensus layer. What we want now is optional proofs on devnets and testnets. What we want next is optional proofs on mainnet by G-Star. And later, we want to investigate and we want to get to mandatory proofs. Getting to mandatory proofs does require a lot more components, and it is the part where we do need to do a lot more investigation. But for optional proofs, we're completely sure that we can do it. You saw Justin's demo, and we want to ship it as soon as possible. Okay, so what is the path forward? You will not get onto mainnet if the zkVMs are not secure. Like, this is the thing that I think we should take away from this talk. Like, if your zkVMs are not secure, by the definition that we've said, it will not get onto mainnet. Any questions?
Here, Kev. We've got this sorted by popularity here, if you want to read through here. So the first two are kind of referencing one another. The first person asked, what will you do to make sure that zkVMs actually ship and not get hung up on research questions and processes? Someone went ahead and asked, they've already done that. Have you seen the demo on ethroofs.org? So feel free to jump in there, or the question's lower.
What is this question?
I think this was just answering that question, suggesting that those two we could probably hide if you want to look at the ones below.
Look at this one?
Yep.
Okay. How do you envision this new architecture transforming the experience of smart contract and application developers? How can compilers and dev tooling make developers' lives easier in this transition? So I'm not sure I understand the question completely. I guess one thing to note is that there are two similar, projects. There's the EVM to RISC-V project, and there's shipping zkVMs that use RISC-V. EVM to RISC-V is more longer term, and this has nothing to do with my talk. Shipping zkVMs on L1s helps the validators or the attesters. So I don't see this affecting smart contract developers currently. I think one thing that might hurt smart contract developers is when we increase the gas repricing of certain opcodes. For example, we might want to increase the gas repricing, the gas cost of Ketchak, for example, and Solidity uses Ketchak a lot. So that's the only place that I see zkVMs possibly affecting smart contract developers. What form of verification standards do you envision? I will leave this to Alexander Hicks, who's not in the audience at the moment. He's basically the lead of this, and yeah, I don't want to misquote him, so I'll leave that question to Alexander Hicks. What will you do to make sure zkVMs actually ship and not get hung up on the research questions and process? This is a good question. Ethereum is a very special place if you want to ship things fast. What we've been doing so far is just trying to integrate into the ACD process or integrate with client core devs as much as possible to make sure that we solve whatever the bottlenecks they think we have. And currently, I think it's going well. We know what sort of the questions, we know what the blockers will be, and we currently have solutions for most of them. I think this is the only way. You just have to integrate, and yeah. When are we going to start thinking in breaking free from CUDA and NVIDIA? Oof. Yeah. Big oof. I'm not sure. I think every zkVM team uses NVIDIA. If you guys can correct me if I'm wrong. I don't think it's a high priority, to be honest, at the moment. What is the consequence of a zkVM implementing a different RISC-V flavor? So you can implement the RISC-V 64 IM none was the minimal. You can implement whatever you want on top of it as long as we support the minimal. The reason why we do have this standardization process is such that the ELs and the zkVMs have a common contract So you don't have one zkEVM being slower, but they support everyone, and then another zkEVM being the fastest, but they only support one EL. Can you get onto mainnet if you're not secure? How will you choose and distribute proof validation systems? So I'll rephrase this question. So when an attester receives the proofs, there's n different proofs. There's n different proofs that are registered on a network, and they need to receive k of them before they say that the attestation, the payload is valid. How do we choose this n? We don't currently know. The reason this process is a bit contentious is because the n proof types that you choose, you're basically choosing ELs that become semi-enshrined into the protocol, whereas right now, if you launch up your Python EL, you can validate the execution payload. So there is this sort of permissioned aspect to adding zkEVM proofs. So we're not currently sure how we're going to choose n, how we're going to choose k, and we're not quite sure what those values are at the moment. Who is responsible for providing security, and how can we help? Currently on our team, we have Cody Gunton. I'd say reach out to Cody Gunton. He's right there. He's putting up his hand. How optimistic are you compared to 6 months ago? I feel like Justin wrote that question. It's not that I'm always quoted as being not optimistic. It's just that I have a lot of questions. I don't like to. I think we know more than we knew 6 months ago. So I would say I'm more optimistic, but I always just have a lot of questions, and I like to be very conservative in things that we're going forward with. I like to be very rigorous in the way that we're thinking about this. I'd say I'm more optimistic now that we've sort of got the proof of concept out that we can do real-time proving. And the thing that we should be focusing on now is security. Like, we just need security. The chain just can't go down. This is one of our requirements. Are those all the questions? Okay, these are all the questions.